Okay, hello again, grade 9. So what we're going to do now is we're going to look at investigation three's answers as well as the questions on page 15 to make sure that you guys know exactly what's potting, and then we can move on to the next section. All right, so make sure that you are on page 14. Make sure you have your pens ready to mark and to change any of your answers. So the results that are going to be in your table after you've set up your PhET simulation and after you've added cells are going to be something like this, guys. All right. So I want you to imagine if one cell is a 1.5 volt. If you add another cell, it's going to be 3 volts. And you add a third cell, it's going to be 4.5. That makes sense, correct? And then your ammeter reading should be something like either 1 amp, 2 amps, or 3 amps, something like that. It should show an increase. The important thing, grade 9s, is that you show an increase. That's the most important thing. So these are expected values. These are not the values that you would have gotten. This would be marked right as long as I can see that they are increasing at the same rate for both the ammeter reading and the voltmeter reading. So you can see the ammeter reading is increasing by 0.1 with every cell. The voltmeter reading is increasing by 1.5 with every cell. So I want to see that rate of change. It needs to be the same. And what are we seeing here? We're seeing a direct proportionality. We're saying that as the voltage increases, the current increases. So the two variables are directly proportional. Now, this is very important, guys. I want you to remember this. This relationship between the voltage and the current is going to remain universal. It's going to remain exactly the same as long as your resistance remains the same. So remember, I told you I wanted you to set that light bulb at 1 ohm. If you went and changed that light bulb to another resistance, it would impact your results. If you change the temperature of the wire, it would impact the results. The diameter of the wire would impact the results, but that's factors of resistance. We'll get to that on Wednesday. The important thing here is that as long as the resistance is constant, the voltage is going to increase. The current is going to increase with the voltage. Okay. Here is an example of the graph that we have put together using the values that we have. And you guys know this already. This should be super easy for you. We are looking at the title needs to have what, guys? It needs to be dependent variable versus independent variable. My dependent variable is my potential difference, which is measured in voltage, and my independent variable is current measured in amps or milliamps, depending on what you're using. Now remember, you guys were supposed to do this in the lab with proper circuit boards. And in that situation, sometimes you get milliamps. You don't get an ammeter reading because the batteries that we have are not always exactly the same. The charge is not always the same. Nonetheless, in this situation, we are using just ordinary amps. So as you can see, as the voltage increases, so does the current. The two work together. Okay, make sure that you have completely filled in this graph. I'm just highlighting this, or attempting to highlight it. It's going a little bit wonky, but make sure that your graph looks similar to my graph, please. Okay. So guys, I think this is what you've all been waiting for, the gradient calculations. So we can see over here from the ones that have been written out by Mr. Ginsberg that resistance is equal to voltage divided by current. So please look at the formula in red first. You will see we write out the formula first. M is equal to the difference in Y over the difference in X. So then the next line, you are going to write your substitution, which is going to be your 2 points. Guys, you can choose any 2 points. The 2 points we chose were the 4.5, okay, voltage, and the 0 voltage. And then we chose for the x-axis 0.3 amps minus 0 amps. So we chose those 2 points as a fixed as a difference. You could have chosen 4.5 volts and 3 volts. You could have chosen 0.3 and 0.2 volts. You could have chosen any 2 points. Okay. You divide that difference and you should get a slope of 15. What this is showing you here is that that rate of change, okay, or that slope is going to be your resistance. So voltage divided by current, so Y divided by X is going to lead to what? Your resistance, or your M, which is 15 ohms. Okay, this will take practice for you guys, but as long as you remember the formula and you remember what the key points, which is difference in Y over difference in X, choosing any 2 points, you will be fine. Okay, let's carry on to the next slide. So we are now looking at the questions on page 15 that I asked you guys to do before you watch this video. The first question asks, what do you think we would, why do you think we would get a constant gradient for the graph? The reason why we're getting a constant gradient is because the graph is a straight line, grade 9s, okay? The gradient does not change because the resistance has not changed. So that rate of change, or the actual predicted increase, is not going to change at all because we did not manipulate the resistance. Okay, so resistance is constant here. So this would be a direct proportion. Therefore, when we have a direct proportion, we are always going to have a constant gradient, a constant slope. Okay, question 2 asks, the graph the graph should pass through the origin. Explain why this is so. When there was no cells, the potential difference is 0. If there is no potential difference, okay, a difference in electrical potential energy, then no current will move around the circuit. Does that make sense? Why it needs to pass through the origin. The origin is 0. So that's saying that there is no voltage. Therefore, there will be no change or no current. Okay. So the next slide, we're going to go into question 3, please. I think it's question 3 and then some conclusions. If you are not ready to go into the next question, please make sure that you change your answers now. Okay, so question 3 asks, what variables do you think should have been kept constant during this experiment? So you already know this. Okay, number 1 is going to be the number of light bulbs. Because what are light bulbs? Light bulbs are resistors. And guess what? We set this up in series. So if you added extra light bulbs, you would be increasing the resistance. Therefore, resistance would not be constant. And therefore, our relationship between voltage and current would not be absolute. Okay, so first things first, number of light bulbs, they need to stay the same, because that is the number of light bulbs. The fact that we only use 1 light bulb tells you that we have kept the resistance the same because it's in series. The temperature needs to remain constant. Okay, the temperature of the connecting wires, the temperature of the light bulbs, have they been sitting there for a long time connected? Okay, we need to start with cool, unused equipment before when we set up our circuit. So remember, these answers have got to do with your circuit boards that you guys were originally supposed to be using. It's got nothing to do with the FET simulation. So this is related exclusively to our circuit boards, but please write it in. Your position of your voltmeter is very important, guys. You can't change it all over the place. Remember, the voltmeter is reading the difference between 2 positions. In this situation, it was reading the voltage that was crossing or going through the light bulb. Your voltmeter, your ammeter, and the cell type that you're using. If you were in the lab and all of a sudden you decided to use a different type of battery, okay, or a different type of ammeter, this is going to impact your results. So these are confounding variables that we keep constant, but they can also have an impact on the experiment. At the bottom of the page, it asks you, what are the conclusions? So I want you guys to write in that, and I've said this already, potential difference and current increase in direct proportion to each other, but only if the resistance remains constant. Therefore, okay, V divided by I is equal to R at a constant resistance. And another way of saying this is voltage and currents are directly proportional. You've done this already in graphing. You know this already. This should all make sense to you. Okay, so that's the end of this video area. But if you guys are struggling at all, please let me know, and we will drop me a message and I can help you out. The next video I'm going to cover is page 16. It shouldn't be that long. We're just going to go through Ohm's law, and we're going to go through the formulas that you guys need to use when you are calculating resistance in series and in parallel.